Morning, good afternoon, wherever you may be in your day. Thank you for choosing to make general chemistry part of that day. There's a lot going on here, so I may break this into two parts, but here's the objectives for both. It's basically to apply our principles for filling orbitals with electrons and to apply them to any element on the periodic table. And to do that in a number of different ways, we're going to represent them in the SPDF notation, noble gas core SPDF notation, orbital diagrams, and through quantum numbers. And without further ado, let's talk about those filling rules. Okay, so we use three basic principles when we describe how and why we fill the orbitals and the subshells the way we do. So, the first of those is the Pauli exclusion principle. I covered that on the end of the last video, I believe. But it boils down to the take-home message is 2 electrons per orbital max. Now you could have 0, you could have 1, but 2 is the maximum. The real rule is that each electron within an atom has a unique set of quantum numbers. Second rule we're going to look at is Hund's rule, and the real rule is you want to maximize spin multiplicity, but the take-home message is you're going to half fill every orbital in a subshell and match spin. Half fill, match spin. So what does that look like? Well, if we were to take a, say, 2p subshell, remember that first number is our principal quantum number, our shell, and the letter represents the second quantum number, or the subshell. So this would be 2p, and p's always come in sets of 3, so we're going to represent those 3 orbitals with dashes. If you look in other videos, or if you look in other textbooks, sometimes dashes are most common, sometimes you use circles, sometimes you use squares. I'm going to use dashes because I think they're less cluttered and easier to draw. So the 3 dashes represent the 3 individual 2p orbitals in the subshell. So going back to that last video, s's always come in 1 orbital in a subshell, p's are 3, d's are 5, f's are 7. So my 3 dashes, and then you would want to half fill each orbital and match the spin. So we have 2 options. Remember, we can have spin down or spin up from the 4th quantum number. Now, this would be the ground state. It's not the only state. Now, I don't want to put the misconception that it's always this way, but this is the lowest energy, this is the ground state, this is the preferred, this is what we'll always use for a test answer. But there are excited states, right? We could flip one of the electrons. This would be half filled but not matching, and this is neither half filled nor matching. So again, that idea, that's a visualization of what Hund's rule is. This is called orbital filling diagrams. We'll do more examples later in the video. The third and final principle is the Aufbau principle, sometimes called the building up principle. But it's basically, we're going to fill the lowest energy. This is going to be the ground state. So lowest energy, and then we go to highest energy. I like to give the analogy of when you pour water into a bucket, it goes to the bottom, you fill from the bottom up. Same thing with these orbitals, same thing with the electrons. They're going to go to the lowest energy well. Okay, which leads to the question, of course, of, well, what is the order of energy of the orbitals within an atom? And that's a very good question you ask. So here's our friendly periodic table, or at least an abbreviated version, and I will actually at some point hold up what I would highly suggest doing on the next test when you rip the back page off. Okay, so if you can go SPDF, which, usually it's embedded in a question for SPDF notation, so not too bad. If you can do SPDF and you can count, you don't even have to count high. If you can count to like 7, you don't even need your toes. You can get all your electron configurations correctly, and the periodic table has all your answers. So let me show you how this works. So SPDF in the order they come. So we want to look at the different rectangles on the periodic table and look in the upper left-hand corner at the number, which I did not put on my fake periodic table, but hydrogen is number 1, boron is number 5, scandium is 21, and down here we're at number 58. Okay, so just look at the order that these rectangles appear. The first one is the S, the second one to appear is the P, the third one is the D, and the fourth one is the F. And you might notice I also went 1, 2, 3, 4. And again, we're just looking at the numbers. Smallest number gets the 1, next smallest to 2, next smallest to 3, next smallest to 4. So again, you'll get very used to this. It's pretty easy to do. But it's S. This is what I'm going to now refer to forevermore as the S block of the periodic table. This 6 wide column is going to be the P block. The 10 In the middle, my transition metals will now be the D block, and down here at the bottom, the lanthanides and actinides will now become the F block. So, what else do we need to talk about? Okay, so you're just going to put a S, P, D, F, 1, 2, 3, 4, intentionally being redundant here, and then just add 1 every time you go down. So 1, 2, 3, 4, 5, 3, 4, 5, 4, 5, 2, 3, 4, 5. You get the idea. You're just counting. So how does this help me get the energy of the orbitals or to list the orbitals? So let's just do a real example. Write the complete SPDF notation for phosphorus. So first thing you need to do is find phosphorus on the periodic table. And this is full, so we got to start at the very beginning. You're just going to go block by block by block across the periodic table, and every time you see one of my numbers I wrote here, or on the test, every time you see one of your markers you write, or the numbers written in marker, we're going to stop and write it down. So I'm here, I see a number, I write the number down and the letter above it. I go to block 2, I go to block 3, number, letter. Block 4, nothing. Block 5, number, letter. 6, 7, or I can't count, but you get the idea. Go across, nothing there. I get the sodium, I write that down. I come over here, I get to aluminum, I write that down, and that gets me all the way to phosphorus. This is the order from lowest energy to highest energy of our subshells, or our orbitals, following the alphabet principle. The last thing we need to do is represent the electrons. So the electrons are going to be represented by superscripts to the upper right of each subshell. So if you've gone all the way across, you just fill completely. So if an S is 1 orbital, 2 electrons max, so 1 orbital becomes 2 electrons. We went 2 blocks over, so this is 2. 2S, we went all the way across, that's 2. And again, you don't even really need to memorize the number, just count. 2P, I went all the way across. 1, 2, 3, 4, 5, 6. 3S, I went all the way across. And 3P, now to get the phosphorus, I went 1, 2, 3. So I put a 3 here. And now we've gotten the right answer. We didn't really have to know any science. All we had to do is know how to read the periodic table. So there's another way, because you can imagine this gets extremely tedious for mercury if you wanted to place all 80 electrons where you kept going and going and going. And all of these inner electrons, and I have another slide that talks about this in more detail, but all these inner electrons are what we call the core electrons. They're completely full. You have a completely even electron distribution, and therefore they're very stable and almost nothing interesting happens there. Remember, the most reactive, the least tightly held are going to be outer electrons. It's going to be the last ones in or the first ones out, if you will. And we call those valence electrons. And those are the ones that really determine all the chemistry of the core. It doesn't really matter all that much. So if we want to do the same thing for mercury, you would find mercury and back it up until you get to the nearest noble gas. In this case, xenon. So you put xenon in parentheses, and that covers your first 54 electrons. We're done with those. Then we go over here to number 55, over here with cesium, and we do the same thing we just did. 6S, I'm going all the way across. 5D, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this throws people sometimes, but realize this goes 57 to 72. What happened here? And if you look closely at what I've been holding up, you notice the little chutes and ladders I did down here on the bottom. Because it's very easy to forget to do this. So just remember to come down here, and I have to add the 4F electrons. And if you write it this way, that's totally fine. And if you write it this way, it's probably better. I will mark both equally correct on a test. But that's how you do it, the truncated version. So you can do the long version, or you can just do the truncated version. The long version is called complete SPDF notation. The short version is called noble gas core electron configuration, or noble gas core SPDF electron configuration. And what you're writing, everything after the noble gas is valence electrons. The noble gas is the core. And if you look closely, this 1s2, 2s2, 2p6 is neon. So you could rewrite phosphorus the same way with neon, 3s2, 3p3. So that's 2 of the 4 ways, the easiest 2 in my opinion, of writing electron configurations. They do require you to have a little bit of knowledge to use them and interpret them correctly, so we're going to talk about that and focus on that with this next piece. But before we do that, let's do two more definitions, paramagnetic and diamagnetic. Paramagnetic, physics definition is attracted to a magnetic field. Chemistry definition is it's one or more unpaired electrons. So it has an unpaired electron. That's the take home. Unpaired electron. If it's diamagnetic, it's dead in a magnetic field. That's how I remember it. Or there are no unpaired electrons. There's a very, very slight repulsion in a magnetic field if you want the physics. But we want paramagnetic, unpaired electrons, diamagnetic. They're all paired up. The only time, because of Hund's rule, they're going to be all paired up is when it's completely empty or completely full, or you have some weird excited state, which, again, I invite you to take upper level chemistry classes and you can talk about things like that. For the sake of this class, empty, full, that's going to be diamagnetic. Everything else is going to be paramagnetic, right? We put one electron in, it has to be unpaired. We put two, we're supposed to split them. We put three in, same idea. I just did a random one here. But this one unpaired electron, this means paramagnetic. Since everything here cancels out, this is going to be diamagnetic. And for the sake of keeping these videos a decent length, as promised, I'm going to cut this video into two pieces. Here's part one, and thank you for your time. Stay fantabulous, everybody.